Chapter 13 Reaction Rates and Chemical Equilibrium. Earlier, we looked at chemical reactions and determined the amounts of substances that react and the products that form. Now we're interested in how fast a reaction goes. If we know how fast a medication acts on the body, we can adjust the time over which the medication is taken. In construction, substances are added to cement to make it dry faster so work can continue. Some reactions, such as explosions or the formations of precipitates in a solution, are very fast. If we roast a turkey or bake a cake, the reaction is slower. Some reactions, such as the tarnishing of silver and the aging of the body, are much slower. We will see that some reactions need energy while other reactions produce energy. We burn gasoline in our automobile engines and produce energy to make our cars move. In this chapter, we'll also look at the effect of changing the concentrations of reactants and products on the rate of reaction. Up to now, we have considered a reaction as proceeding in a forward direction from reactants to products. However, in many reactions, a reverse reaction also takes place as products collide to reform reactants. When the forward and reverse reactions occur at the same rate, the amounts of reactants and the products stay the same. When this balances the rate of forward and reverse reaction is reached, we say the reaction has reached equilibrium. At equilibrium, both reactants and products are present. Some reaction mixtures contain mostly reactants in the form of few products, whereas others contain mostly products and a few reactants. Section 13.1 Rates of Reaction. For a chemical reaction to take place, the molecules of the reactants must come in contact with each other. The collision theory indicates that the reaction takes place only when molecules collide with the proper orientation and sufficient energy. Many collisions can occur, but only a few actually lead to the formation of product. For example, consider the reaction of nitrogen and oxygen molecules. To form nitrogen oxide, the collisions between nitrogen and oxygen molecules must take place the atoms in the proper alignment. If the molecules are not aligned properly, no reaction takes place. Activation energy. Even when a collision has the proper orientation, there still must be sufficient energy to break the bonds between the atoms in the reactants. The activation energy is the minimum amount of energy required to break the bonds between the atoms and the reactants. The activation energy appears as an energy hill. The concept of activation energy is analogous to climbing a hill. To reach a destination on the other side, we must have the energy needed to climb up to the top of the hill. Once we're at the top, we can run down the other side. The energy needed to get us from our starting point to the top of the hill would be our activation energy. In the same way, a collision must provide enough energy to push the reactants to the top of the energy hill. Then the reactants may be converted to products. If the energy provided by the collision is less than the activation energy, the molecules simply bounce apart and no reaction occurs. The features that lead to successful reaction are summarized next. 3 conditions required for a reaction to occur. Number 1, collision. The reactants must collide. 2, orientation. The reactants must align properly to break and form bonds. Number 3, energy. The reaction must provide the energy of activation. Reaction rates. The rate or speed of reaction is determined by measuring the amount of reactant used up or the amount of product formed in a certain period of time. The rate of reaction is the change in concentration or reactant or product over the change in time. Perhaps we can describe the rate of reaction with an analogy of eating pizza. When we start to eat, we have a whole pizza. As time goes by, there are fewer slices of pizza left. If we know how long it took to eat the pizza, we could determine the rate at which the pizza was consumed. Let's assume 4 slices are eaten every 8 minutes. That gives you a rate of a half of a slice per minute. After 16 minutes, all 8 slices are gone. Factors that affect the rate of a reaction. Some reactions go very fast, while others are very slow. For any reaction, the rate is affected by changes in temperature and in the concentration of the reactants, and by the addition of catalysts. Temperature. At higher temperatures, an increase of kinetic energy makes the reacting molecules move faster. As a result, more collisions occur and more colliding molecules have sufficient energy to react and form products. If we want food to cook faster, we use more heat to raise the temperature. When body temperatures rise, the pulse rate, the rate of breathing, and the metabolic rate all increase. On the other hand, we slow down reactions by lowering the temperature. We refrigerate perishable foods to retard spoilage and make them last longer. For some injuries, we apply ice to lessen the bruising process. Concentration reactants. For virtually all reactions, the rate of reaction increases when the concentration of the reactants increase. When there are more reacting molecules, more collisions that form products can occur, and the reactant goes faster. For example, a person having difficulty breathing may be given oxygen. The increase in the number of oxygen molecules in the lungs increases the rate at which oxygen combines with hemoglobin and helps the person breathe more easily. Catalysts. Another way to speed up the reaction is to lower the energy of activation. The energy of activation is the minimum energy needed to break apart the bonds of reacting molecules. If a collision provides less than the activation energy, the bonds do not break and the reactants molecules bounce apart. A catalyst speeds up the reaction by providing an alternative pathway that has a lower energy of activation. When activation energy is lowered, more collisions provide sufficient energy for reactants to form product. During a reaction, a catalyst is not changed or consumed. Catalysts have many uses in industry. In the manufacturing of margarine, hydrogen is added to vegetable oils. Normally, the reaction is very slow because it has high activation energy. However, when platinum is used as a catalyst, the reaction occurs rapidly. In the body, biocatalysts called enzymes make most metabolic reactions proceed at rates necessary for proper cellular activity. Enzymes are added to laundry detergents to break down proteins. Proteases, starches, greases that stain clothes. Such enzymes function to lower the temperatures that are used in home washing machines, and they are biodegradable as well. The factors of reaction rates are summarized in Table 13.1. Factors that increase reaction rates. Increasing reactant concentration because of more collisions. Increasing temperature because more collisions and more collisions with energy of activation, and adding a catalyst because it lowers the energy of activation.